Solubility equilibria is going to be our next topic. Will it dissolve? And if not, how much of it will dissolve? All dissolving is an equilibrium problem. If there is not much solid, it will all dissolve. As more solid is added, the solution will become saturated. So the solid goes back and forth between being dissolved and being a solid. The solid will precipitate just as fast as it dissolves. This is an equilibrium. It's where it's going back and forth at an equal rate. The general equation for an equilibrium problem will be using M plus. This is going to stand for a cation. This is usually a metal, that's why it's M. And then NM minus stands for an anion, which is usually a nonmetal, basically always nonmetal. Here's a general equation. We have M to A, which is going to be the number of moles or how many, just like a subscript, and then NM to B, again another subscript, and then it's equilibrium, so we have a back and forth arrow, and then let's go a little bit closer. We're going to have A, again, our number of moles, and B, our number of moles coming in front. So these little numbers right here are now coming in front. And that will be M plus, so the metal cation, and it's an aqueous solution now, plus B, the non-metal, and it's aqueous cation. So this is our general equation. This one's a solid, and these ones are aqueous. That's important. So if we're looking at equilibrium in general, we always put our products over our reactants. So we have K is equal to M, the metal raised to its number of moles, the non-metal raised to its number of moles, divided by the salt itself. Or you could just simply looking at it on top of each other would look like this. But the concentration of a solid does not change, so therefore we do not include it in an equilibrium expression. So our constant K is going to be excluding our salt. So therefore the bottom here will get canceled out. So it'll be M plus raised to the number of moles, and then our cation raised to its number of moles. This is what we call the solubility product for each of the compound, and the solubility product is known as KSP. Alright, so here we have here are some expressions we can use for KSP. So here we have our salt, we have silver chloride, and we have its equilibrium going back and forth. We have our silver and our chloride. So we have KSP is equal to Ag times Cl minus. KSP is constant for a reaction. So again, we can find these constants on the table you guys have before this on your notes. And so again, this number is going to be found on a table. Then we have lead 2 chloride, and this will go back and forth between being lead plus 2 and chlorine. Again, this one right here, we have a 2, so therefore when we write our expression here, it's going to be raised to the squared. So our KSP is equal to the concentration of Pb times the concentration of chloride squared. And the constant for this is 1.7 times 10 to the -5. Again, these can be found in your table. Alright, so how can we calculate solubility? We have academic class. You guys can stop watching the video right now if you're watching it for supplement. If you're in honors, which most of you are, please go ahead and continue listening. We're going to be calculating of the concentration of a 1 ion, knowing that other part. So we have to know at least one part of our concentration to be able to determine this. So I know what is the concentration of lead, because again, their brackets mean concentration or molarity. So our molarity of lead in a solution in equilibrium with lead chloride if the concentration of chloride is equal to 0.02 molarity. Alright, so here we have a reaction. So I'm going to go ahead and just move up so we can see this with the reaction working out. So here we have our reaction. And here's it is with the concentration. So you have the concentration of lead times the concentration of chloride squared equals to KSP. Then what we're going to do is we're going to plug that in. So we know 0.02 is our molarity. So we're going to plug our 0.20 in, and we're going to square that right here. And also because it had 2 moles of it. And that will equal this. Then we're going to go ahead and square that. When we square it, we get 0.0024. And I apologize for that glare. There we go. And that is going to equal 1.7 times 10 to the -5. Then to be able to solve this problem, to get Pb by itself, we're going to have to divide both sides by 0.04. So these two will cancel. And we take 1.7 times 10 to the -5 divided by 0.00004. And therefore the concentration of lead becomes this molarity. Alright, so that would be the answer there. So let's do some more problems. So calculating solubility. How can we calculate how soluble something can be? This will be is determined by its equilibrium. So this will be an equilibrium problem again. We want to calculate the solubility of SrSO4 with a KSP of 3.4 times 10 to the -7th molarity. This is so knowing this equation, we'll have to be able to write an expression of how SrO4 breaks down. So SR, SO4, the reaction is going to make it so it's SR 2 plus reacting with SO2 minus 2, SO4 minus 2. So let's go ahead and if we write an equilibrium expression for this, we would put our products on top, raised to their respective powers, over the reactants. So let's go ahead and let's look at, but this is going to be an equilibrium, and then this is a solid. These are aqueous, so our products don't matter. So it'll only be our reactants matter, only our products. So let's go over here. Here's a problem already worked out for us. We have our equilibrium right here, and then again, we don't worry about it if it's a solid. So we can ignore our solid, but we are going to worry about our anions. So KSP is going to equal the concentration of SR times the concentration of SO4. When we're talking about the solubility, we can assume that the concentrations of both of these are going to be the same. If they're going to be the same, we can say they're the same variable, or they're both X. So here we're plugging in an X for SR, and here we're plugging X in for SO4. When we do that, our KSP is now equal to X squared. Again, we knew the concentration for lead looking at our chart, and it was also given to us in this problem. Nope, it was also given to this problem. That's correct. It's also given to us in this problem. So we're going to have it now 3.4 times 10 to the negative 7th equals X squared. So we're going to take the square root of both sides to be able to solve for X, and eventually we'll get out X equals 5.84 times 10 to the negative 4th. All right, we have another problem very similar to that. We want to calculate the solubility of silver chromate with a KSP of 1.2 times 10 to the negative 12th. So we're going to have to worry about this problem very similarly. We need to write a reaction first. So we're going to start with our silver chromate reacting to form two silvers, because we had two here, so therefore we have to put 2 moles of it in front. And then it has a +1 charge, and then we're going to add CrO4 to it as well, and that only has one of those because there was only one being used. This right here is a polyatomic ion. That's how I know to leave it by itself, not split them up into all of their individual pieces. Again, this one's always going to be a solid because it's a salt, and these are going to be aqueous, so they're going to be included in KSP. So we have our KSP is going to be equal to silver, and this time it's squared because we had 2 moles, and we knew there were 2 moles of it because of this 2 right here. Then we have it multiplied by the concentration of our chromate ion. Again, we can assume the concentrations of both these are going to be the same at equilibrium. So therefore we can call each concentration inside of here X. So we're going to put X, and this time it gets squared because there's a 2 there, times X. This gives us X cubed. And then we were told what the KSP value was, which is 1.2 times 10 to the negative 12th. So to be able to solve this, we are going to have to take the cubed root of this. So we're going to take the cubed root of X cubed to get X to just be X, and take the cubed root of 1.2 times 10 to the negative 12th. When we do this, we get 1.06 times 10 to the negative 4th equals X. So the common ion effect, this is just the last thing, if we try to dissolve a solid in a solution with either the cation or the anion already present, less of the product will dissolve. So if you already have stuff already dissolved in it, less of it will dissolve later. Do your quizzes.